What's up, y'all? Welcome back to another video of studying with Charles and his friend. My name is Daniel Chen, and today I'll be covering over IB Chemistry Structure 2.1 models of bonding and structure. Specifically, we're looking at the ionic model today. So, table of content. So, in Structure 2.1, the ionic model, we'll be covering four main ideas: formation of ions, ionic bonding, structure of ionic compounds, and physical properties of ionic compounds. Starting with the content, Structure 2.1, formation of ions. So when talking about formation of ions, there's two key concepts to consider. First of all, is the cations and anions. Cations are formed when atoms lose electron. Losing electron means positive charge. For example, if sodium today lose one electron, it means plus one charge, so Na plus. An ion on the opposite side is formed when atoms gain electron. So gaining electron means negative charge. For example, Cl, if it gain one electron, it becomes Cl minus. Technically, it's 1 minus, but we don't write the 1. So when gain one electron, you minus one charge. And this kind of idea of lose one electron, gain one electron, and plus one charge and minus one charge can be multiple, right? So lose two electron means plus two charge. Gain two electron means minus two charge, so on and so forth. And the second key concept is oxidation number. So oxidation number basically represent the charge of the atom. For example, how do I determine the charge of a hydrogen atom? So I looked at the oxidation number, right? So oxidation number is labeled up here on top of each group of a periodic table. We skip the transition metals. So in group 1, we have 1 plus. Group 2, 2 plus. Group 13, 3 plus. 14, 4 plus or minus. 15, 3 minus. 16, 2 minus. 17, 1 minus. And 18, 0. These numbers represent the charge. And this would be further applied in later unit when we actually talk about ionic bonds. So going into ionic bonding. So to understand what are ionic bonding, it is essential for us to learn how ionic bonds form. So ionic bonds form when metal lose electron, where it form cations, and nonmetals gain electron, where it form anions, and these two opposite charge attracts, forming ionic compounds. This will definitely be on the test, so you should consider remember it. The definition of ionic bond provided by the IB is electrostatic attraction between oppositely charged cation and anions. Missing any part of this definition or like this explanation will cost you mark. And these questions often appear on the 1 mark paper 2 questions. So losing any part of the definition means you lose 1 mark. So you might as well remember it to gain that 1 mark, right? It is important to note that ionic bonding is not the same as electron transfer. Ionic bonding is electrostatic attraction after the ions are formed, where electron transfer creates the ions. So going deeper into ionic bonding, the structure of ionic compound is a giant ionic lattice. So it's regular repeating arrangement of ions. There's a strong attraction in all directions. So as you can see on the diagram on the right, for each cations, there's 6 anions around it. So on 6 sides, so like 3 dimension, right? So cations, front, back, top, down, left, right. So the properties caused by ionic bonding are high melting point and boiling point because of the strong lattice force. It's brittle, like charges repel when layers shift. It conducts electricity only when it is in liquid form or it is dissolved in water, so like aqueous, right? Because ions are free to move. And it is usually soluble in water. So how exactly do we write chemical formula for binary ionic compounds? So we are not considering transition metal in this case. So the step-by-step method will be step 1, write the ions with their charges. So for example, magnesium and oxygen is Mg2 plus and oxygen 2 minus. And you might ask, how do I determine the charge? Where do I get the charge? As mentioned earlier, the charge is represented by the oxidation number. So as the image on the right, you can see magnesium on group 2 have a 2 plus charge. Step 2 of the method will be swap and drop. And in some other textbook, it might be referred as the crisscross method. So you bring the numeral value of the charge down as a subscript. You do not bring the sign. Simplify if needed. So in this example where we use Mg and O, we bring the charge of Mg down as a subscript for O, and we bring the charges of O down as a subscript for Mg. So it creates Mg2O2. And as referred here, you need to simplify if needed. So 2 and 2 obviously can be simplified as 1 and 1. So MgO. Some of the important rule is that we write metal first, non-metal second when we are writing the names. And we never write charges in final formula. So there's no plus, there's no minus in the subscript. We reduce the subscript to the simplest ratio. So as shown here, the ratio is originally 2 to 2. Then we reduce it to 1 to 1. And if the crisscross method give 1, don't write 1. So like when Na plus and Cl minus, when we crisscross, it creates Na1, Cl1. So we don't write the 1. For practice, please write the formula for each binary ionic compound. So you might want to pause the video here to write down these compounds. So here's the answer. So as an example, I will do a few. So for example, in magnesium and nitrogen, Mg is in group 2, right? So the oxidation number is 2 plus. N as a nitrogen is in group 15. So the oxidation number is 3 minus. We do our crisscross method, right? So the charge of Mg become the subscript of N, where the charge of N become the subscript of Mg. So we can see Mg3N2. So the charge of N become the subscript of Mg, and the charge of Mg become the subscript of N. So moving forward, we need to start considering writing a chemical formula for binary ionic compounds with transition metal. It is not that different from writing one without a transition metal. It is just that we need to start considering the charges of transition metal. So as mentioned in the front, transition metal's charge can't be simply decided by oxidation number, where we use a single constant value to decide the charge. Transition metal can have multiple possible charges. So the Roman numeral at the end of each transition metal tells you which ion it forms. For example, FeII. II in Roman numeral means 2, so Fe2 plus. FeIII. III means 3, so Fe3 plus. Same for Cu, Cui. I means 1 in Roman numeral, so it's Cu plus. So we first write the two ions with charges. So metal cation first, non-metal anion second. And of course, at this case, if it is ionic bonding, the transition metal will always come first as it is the metal. So for example, we write Fe3 plus and O2 minus. Again, we use the crisscross method, and we bring the charges of each ion down as a subscript following all the rule mentioned previously. So the charge of Fe down for the subscript of O, and the charges of O bring down as a subscript of Fe, crisscross. We reduce the subscript to the simplest ratio, but in this example, 2 to 3 is already the simplest ratio, so we do not need to simplify further. At last, do not write charges in the final formula, as mentioned previously in the ionic bonding, right? We don't want the charges. So here are some practice. of writing formula for each ionic compound with transition metal. You might want to choose a few to try it out to make sure you understand, and you might as well pause the video here to practice some of the formula writing. So this is the answer. If you follow our method of first identifying the charge for the cation, which is the transition metal, then we do the crisscross, then reduce, then you should be correct in all these. Then we move on to polyatomic ions. Polyatomic ions are made out of more than one type of atoms. They are generally negative ions, although there are some positive ones such as ammonium ions, which is an exception. These polyatomic ions, you must remember them on a test. It is not provided in your formula booklet, but it is essential for you to know these, especially knowing the overall charges, their formula, and it is essential when you want to do bonding with polyatomic ions. Determine the formulae for the following ionic compounds. Ammonium sulfate. So ammonium NH4 is a polyatomic ion with a charge of 1 plus. As mentioned above, this is exception. It is normally negative, but ammonium is an exception. Ammonium have 1 plus charge. Sulfate SO4 is a polyatomic ion and has a charge of 2 minus. So we again use the crisscross method, and be careful. The polyatomic ions need to be placed in bracket if it is more than one charge. So we do the crisscross, right? So the charge for sulfate, which is 2 minus, become the subscript for NH4. And as it is more than 1, we need to put NH4 in a bracket, then write the subscript, and SO4 as the charge is 1, so we don't put it in a bracket. So remember, polyatomic ions are ions that contain more than one type of element, such as OH minus, right? So if more than one polyatomic ions is needed in a chemical formula, it is placed inside a bracket with the number of them outside the bracket. So after learning about how to turn names into formula, we want to also learn about turning formula into names. On actual exam, we won't actually see like iron 3 plus oxygen. We will see iron 3 oxide. And how do we exactly turn iron 3 oxide into formula, or turn formula into iron 3 oxide? So turning formula into name. So the first step is identifying cation. So it is normally the first element, and if it is a metal with a fixed charge, for example, +1 parts 2 +3, all with the oxidation number, keep the normal name. Example, Na plus, sodium, Mg2 plus, magnesium, Al3 plus, aluminum. They all have a fixed charge. They are not transition metal. Second, identifying the anion, which is the second element. So if it is a non-metal, we change the ending to IDE. So oxygen, change to oxide. Nitrogen, change to nitride. Sulfur, change to sulfide. Chlorine, change to chloride. We change the ending of IDE for non-metal. If it is a polyatomic ion, just state its name. State its normal name. So SO4 2 minus, sulfate. SO4 minus, nitrate. CO3 2 minus, carbonate. Just state its name. So what if the first element, which is a cation, is a transition metal? What do we do with it? So the rule with transition metal is that we use the oxidation number, and we apply the rule of total positive charge equal total negative charge. So for example, in this iron chloride 3, chloride have a fixed charge of 1 minus as gotten from the oxidation number. So 3, as we can see, there's 3 chloride, so 3 times -1 equal -3 in total charge. So the total negative charge need to equal the total positive charge. So we must have +3 charge. So iron must be +3. So What is its charge? Plus 3. So ion 3 chloride. So we put the name together, cation first, add numeral if it is transition metal, then anion. To review the steps, we first identify the cation, second identify the anion. For third, if the cation is transition metal, calculate the oxidation number, and as fourth, put the name together. So for example, we have Al2O3. So we first identify if there's transition metal. Is there? No. Is there polyatomic ions? No. So for the cation, we just state its name, so it's aluminum. For the anion, we change the ending to IDE, so oxygen to oxide, and we combine it, aluminum oxide. In the second example, we have CuCl2. Is there a transition metal? Yes, Cu is a transition metal. Is there a polyatomic ion? No. So because Cu is a transition metal, we need to use the anion to find the oxidation state. Cl is chlorine. We need to change its name to chloride. What is the charge of chlorine? -1, gotten from the oxidation number. Because there's 2 chlorine, so we times 2. So -2 for the total negative charge. Because the total negative charge need to equal to the total positive charge, so Cu must have +2 charge. So Cu2 chloride. In this harder example of Fe2O3, is there transition metal? Yes. Is there polyatomic ions? No. So because Fe is a transition metal, we need to use the anion to find its oxidation state. Oxygen is oxygen. We change its ending to IDE, oxide. So the charge of oxygen is -2, gotten from the oxidation number. So we have 3 oxygens, so we have 3 times 2 equals -6 charge. Because the total negative charge need to equal to the total positive charge, so the total plus charge must be +6. Because there are 2 Fe atoms, each of it can have 3 plus charges. So like +3 times 2 equal +6 equal the total charge. So combine it, iron 3 oxide. In this even harder example, we have FeSO4. Is there a transition metal? Yes. Is there a polyatomic ion? Yes. So Fe is a transition metal, so we need to use the anion to find its oxidation state. SO4 is sulfate because it is polyatomic ion, so we don't need to change its name, right? We just state its name. So the negative charge for SO4 is -2. And the sulfate is -2, so the Fe must be +2 as the total negative charge equal to the total positive charge. So it becomes iron 2 sulfate. So for practice, write the name for each ionic compound. You might want to pause the video and write it in your notebook. And here's the answer. So structure 2.1.3, part A, structure of an ionic compound. So when talking about structure of ionic compound, as covered before, it is a lattice structure. So each cation have 6 anions surrounding it on a 6th side. And the strength of an ionic bound compound basically mean how strong the electrostatic attraction is. So ionic bond strength can be depending on 2 factors. First, magnitude of the charge on the ions. Second, the size of the ions, which basically mean the distance between the ions. So higher the charge, stronger the attraction. So vice versa. Lower the charge, lower the attraction. So for size, smaller ions closer together, stronger the attraction. Larger the ion, further apart, weaker attraction. And here are some examples. So to better visualize the strength between ionic bond, we want to look at its lattice enthalpy. So the lattice enthalpy is the energy required to separate 1 mole of an ionic compound into its gaseous ions. So lattice enthalpy is the energy required to separate 1 mole of ionic compound into its gaseous ions. It measures how strongly the ions are held together in the lattice, so more energy required, stronger the ionic bond. The relationship between lattice enthalpy and the ionic bond strength. So ionic bonding is the electrostatic attraction between the cation and the anion, right? So the stronger the attraction, the higher the lattice enthalpy is. Stronger the ionic bond, higher the lattice enthalpy. Small ions, highly charged ions. Vice versa. Weaker the ionic bond, low lattice enthalpy. Large ions, low charged ions. So to better visualize this relationship, we want to look at this formula. You don't actually need to know this formula, but I thought it would be helpful if we can apply this into our calculation of enthalpy. So in this formula, KNM divided by Rm plus Rx. The K represent a constant depending on the lattice structure. We do not need to know this. We need to know is the N and M represent the charges of an ion. So we are doing magnitude only, no plus or minus. And the Rm and Rx plus and minus are the ionic radii. So effect of ionic charge, so the N and the M. So the numerator is N times M, the product of the charge. So the higher the charge, much stronger the attraction, higher the lattice enthalpy. So for example, in compound NaCl, the charge is +1 and -1. Multiplying their magnitude, which is 1 and 1, give us 1. So it has a weak lattice enthalpy strength. So compared to MgO, which have +2 and -2, multiplying its magnitude, 2 times 2 equals 4. So compared to NaCl, it have a stronger lattice enthalpy. So what is even stronger is Al2O3, right? Aluminum have a charge of 3 plus, oxygen 2 minus. So multiplying their magnitude give us 6. So even stronger. So the ionic radius. The denominator is the sum of ionic radii. So the lower the denominator, the higher the lattice enthalpy, as it is an inverse relationship. So the smaller the ion, the smaller the distance, stronger attraction, higher enthalpy, vice versa. Explained in the periodic table trend as mentioned in previous video on periodic table trend, going across period means ions getting smaller, lattice enthalpy increases. Going down in a group, ions get larger, lattice enthalpy decrease. So that's it for today's video. Thank you guys for watching. If you have any question, please comment below and we will try to respond as soon as possible. As this is my first video, sorry if some part is kind of confusing or not explained that well. Please do comment if you think some part can be improved. Please like and subscribe if you find this video helpful overall. And to get notification, please open the bell. You will get notification when we have a new video. So yeah, good luck guys for chemistry 2.1 exam. Manifest for a 7. Let's go.